In a previous video, with a simple drying example, I promised to come back to you on why it is unrealistic to assume 100% relative humidity in the outgoing air from the dryer. If you have watched my video on drying rate for hygroscopic and non-hygroscopic materials, you have perhaps already understood the reason why the outgoing air can't reach 100% relative humidity. It is because the driving force approaches zero for both mass transfer and heat transfer. But instead of drawing schematic lines in a diagram like we did in that video, let us now look at mass transfer from a more mathematical point of view. Consider a fully wetted surface with a width b, along which an airflow g kilogram of dry air per second flows. Let x be the water content in the air at a given point. Let us assume that we have steady state conditions and that the conditions infinitely close to the water surface is at equilibrium. This means that the water temperature is the adiabatic saturation temperature of the air. But since it's easier to say wet temperature, and since adiabatic saturation temperature and wet temperature is the same essentially for moist air at modest temperatures and modest water contents, let us just call it the wet temperature. The dry temperature of the air infinitely close to the water surface will equal the wet temperature, since two phases in equilibrium with each other by definition have the same temperature. The water content in the air infinitely close to the water surface is xW, the water content at saturation. Now, study a thin slice dz of the water surface perpendicular to the airflow. How much does the water content of the air change when we cross this slice? One way to express that change is to express the airflow g times the change in water content dx, that is g times dx, using mass transfer coefficient sigma. We get g times dx equals sigma times the difference in water content, that is xw for air close to the surface, minus x for the bulk air. To get to the same unit as g times dx, we multiply with the area dA of the slice. Note that dA equals b times the thickness dz of the slice. What we get is a separable differential equation. If we shuffle around, we have z equals g divided with sigma and b times the integral from x in to x out of dx divided with xw minus x. After integration, we get the length of z of the dryer as g divided with sigma and b times the natural logarithm f of xw minus x in divided with xw minus x out. So let's try to calculate the required dryer length if the outgoing air has a relative humidity of 100%. So if the outgoing air has a relative humidity of 100%, this means that the water content x out equals xw. However, in the equation we just derived, we divided with xw minus x out, which now proves to be xw minus xw, that is 0. This means that we need an infinitely long dryer to achieve 100% relative humidity in the outflow, which is clearly not a reasonable length. Let us now go back to our example and recalculate with a more realistic relative humidity of 80% instead in the outgoing air. When we change our graphical solution, we see that A, the change in water content x3 minus x2 decreases. We will thus need more fresh air. B, the outgoing air is slightly warmer, which means we will need more energy. And C, the evaporated water is also slightly higher, it having the same temperatures as the outgoing air, and thus a bit more energy is needed. Our new x3 is approximately 0.019 kilogram of water per kilogram of dry air, and through a mass balance shown here, we calculate our new g as 11,765 kilogram of dry air per hour. Our previous result was 10,526, so the required airflow increased by 12%. Our enthalpies H2 and H1 has not changed, so through an energy balance we can calculate our new energy demand as 12% higher than before, 108 kilowatts.